And welcome to our Splinter session from solar to stellar, establishing high-fidelity stellar data sets that isolate individual sources of variability. So this has been organized by Jacob Luhn, Lily, Zhao, and myself. I'm sorry. So I'm just standing up here representing the three of us. And I just want to go for a few minutes just to sort of prime us up for what this Splinter session is about. Most of the Splinter session is going to be active discussion. We've got a few talks coming up first up just to kind of prime our minds, get us in the mindset of what we're trying to achieve here. So the driving question behind this Splinter is what stellar data sets will allow the community to produce the largest advances in probing stellar activity and stellar variability, developing new stellar variability diagnostics, and also assessing different mitigation techniques. So having benchmark data sets in which we can compare our mitigation techniques. And also on top of this, how we can facilitate communication between instrument teams to try and build these data sets. Where are we going to get these data sets from? What we'd like to get out of this session with all of your participation is to get some initial target lists or an idea of targets that we want for being stellar variability touchstones. So what is a nice example of pulsation? What's a nice example of XYZ phenomena? We also would like to start the idea of having a stellar variability working group. You know, there's a lot of us here. We all understand now in the era of EPRV that stellar variability is really important. So getting, you know, a nice communication network of people together to talk about stellar variability and share our ideas. And it would be kind of nice as well to get a white paper together from the discussions from sort of the community that's here about what we can do. Our session format, as I said, we're going to have some introductory talks for the first little bit. So I need to get off the stage because I'm already 6 seconds over, and a group discussion for the majority of this. So we will get you guys to split up into groups in a bit after the talks, and we'll have a discussion. All right, so first up, to get us in the mindset of stellar variability, I'd like to welcome Michael Crétinier up onto the stage to give us a primer of what sources and timescales of stellar variability we care about.
Okay. Hello, everyone. So I have the difficult task to try to explain to you all the physical processes that are acting at the surface of the star. And I think one thing that we can say is that when we were in high school, at least in physics, we all learned that when we design an experiment in physics, we only play with one parameter. The problem is that we cannot build star, so we have to live with that, and you have different processes that are acting at the surface of your star. So you see, you have the stellar pulsation, you have the granulation, you have active region because your star are rotating, they are breaking the balance at on your stellar surface, and everything is evolving on longer time scale. Of course, all of them are also acting on different time scales. So we are going from few seconds towards years, and also with different amplitude. And this is one thing that we can play with basically is, for instance, the time sampling of the observation. I will focus on the effects, for instance, about at the rotational period, because even at the rotational period, things can be complex. We all know that we have the flux effect, which is simply the fact that you have active regions that are breaking the balance between the receding and approaching side of your star. And you have also the inhibition of the convective blue shift. And those signals are summing up in radial velocity, and it's quite difficult to disentangle them. And typically, if you can think about a design or a star that you would like to observe, the flux effect dominates for fast rotating star, whereas the inhibition of the convective blue shift dominates on slow rotating stars. So it can have an implication about the kind of star that you want to observe. One thing that we know about stellar activity is that, I mean, the sun or any star basically are not simply solid body objects. We are observing a plasma, and it has a lot of implication typically about the wavelengths that you would like to observe and the physical process that you would like to study. And so for that, you can also use different band paths typically to probe the different layers of your star. Or actually, even when you look at single stellar lines, we know that the continuum is formed deeper into the star than the core of the line. So you saw already the talk of Khaled Al-Mula yesterday, and you can even actually study a single stellar line to probe the different layer of your star. It's nice because then if you use that, you can begin to somewhat probe the physical process which is happening on your star. And here you see the line bisector in the quiet star. So we see that deep into your star, so closer to the continuum, the bisector is more blue shifted because the flow are faster. And you can do that for all the stellar lines. It has been shown by Reiners. You see exactly the same effect on all of them. And now so again, deep lines less affected than shallow lines. And when you have an active region, for instance, in the context of the inhibition of the convective blue shift, you change your bisector. And this has been shown again a long time ago, 40 years ago by Cavallini, that your bisector is redshifted towards, it's redshifted. So one thing is that I think we are all somewhat in agreement that we have to go back to somewhat leave the CCF domain to try to go back to the spectrum, because this is where the information is. It's on your spectrum, and it has a lot of implication about the signal to noise ratio of your observation. And typically, if you want to measure distortion of your line profile, it can be the change of the depth, the width, the bisector. It has implication about the signal to noise ratio that you target. And I will just present to you one data set, which is quite known for stellar activity. So if you look AlphaSen B in 2010, it had been observed by ARPS with really intense strategy. You see it is really nice modulation at the rotational period of the star. And it's quite nice because also when you observe star, it's not guaranteed that you have a so nice modulation, because it depends on where your active region are or how your active region are distributed at your stellar surface. And in that case, it looked like all the active regions were somewhat packed in a nest. And actually, you can see the number of studies that already investigate that data set. I'm pretty sure that there are still people working on it. And it's basically showing to you, when you have a good data set, the kind of science that you can do. And it will be, it was my last point. So thank you.
So since this will be a discussion focused session, we will be saving questions until the end. Even though now there will be an awkward silence as we get the slides up again. And so for this next part, I wanted to run through a few slides. I talked about what we have learned so far from the solar data sets and how we might want to apply this to when we're thinking about the stellar target list we want to compile during the stellar session. And so I showed a bunch of slides just yesterday comparing the different solar telescopes from Express, NUID, HARPS, and HARPS North. And I showed them bin. And here I'm showing actually just one day with all of the observations on bin just as they came out from the data pipeline. And so you can see, for example, HARPS in orange has like these 1 minute cadence. And so they fall, you see them much more often than the HARPS North, for example, just have every 5 minutes. But even without the binning and like the building the signal to noise, you can see a lot of the same patterns. These P modes that got averaged out when we bin to 5 minutes are present and are agreed upon between the different instruments, which is to say instruments are agreeing very well, as I mentioned yesterday. And so there is a lot of benefit to combining data from different instruments, getting more time coverage and building up the signal of things that we care about. Instruments are agreeing very well, but of course it's possible that they could agree more. So some of the things that's worth thinking about when we're thinking about the different instruments and targets that we want to include in this list is that instruments do differ in things like wavelength range. Also the signals of each lines as the throughput as a function of wavelength will change for different instruments. And the blaze will somewhat slightly change, even though most of the blazes of these instruments, at least, which use a similar shell grading, do line up quite well. And there's an infinite number of other ways that instruments will change. One pixel will be good on one instrument, maybe a little bit less good on other instruments, et cetera, et cetera. And so depending on how low you go, you could continue to list all of these different changes that might affect the RVs. But again, big plot, most of them are doing well. And so it is worthwhile to compare data from different instruments. And the differences in the instruments, even though we can't even enumerate all of them, is something we will be able to probe with the solar data set that we currently have and are collecting. And so it's definitely not a competition, but if it were a competition between the sun and other stars, what are the kind of benefits that we get from observing these two different stars, right? When we observe the sun, we obviously get these extremely high SNR data, and also because it's so bright and so easy to observe, we get extremely high cadence, extremely regular data sets. With the sun, we also know of all the planet signals, planet 9 aside, that we can remove from the data set, and we have a lot of data observing the sun in different ways, and so we have a very good understanding of the stellar surface. And this, with all of this known properties, it allows us to benchmark across the different instruments, which all happen to be observing the sun at the same time. However, when you observe a star, that gives you the benefit to probe the complete optical path. Most solar feeds don't go through the telescope, of course, otherwise they would burn the mirrors. And so there's a bit of the optical path that's messing, but most do feed up into the front end module and start from there for the instrument half. When you observe a star, it will be identical observing conditions for if you're observing a possible extra solar host star. And of course, with the stars, you have a variety of stellar types. And so if you kind of compare the two, with the sun, you can't do anything, right? It's going to remain one star with one type of stellar activity that might change an activity cycle and manifest different types of stellar activity, but it will still be the activity of just the sun as one type of star. When you observe the sun, there are some differences in how you observe it, such as the differential extinction that we've mentioned, and also the tellurics will behave differently in solar observations than with stellar observations. And those differences are something you will have to contend with when you're testing different pipelines. And as I mentioned, it only probes most of the optical paths. And so if you're interested in understanding how the light travels through your complete optical path, it will change a little bit. But if we think about all the benefits we get from the sun, there are some ways that we can recreate it with stellar observations. If we want the high SNR, perhaps maybe on the target list, what we really want to focus on are the brightest stars, where we'll be able to get a similar SNR for across a lot of different instruments with different throughputs. Maybe cadence, if we wanted to capture these P modes, we need to start thinking about ways that this community can motivate really daring observing proposals that take up an entire night of telescope time to look at a 4th magnitude star at a 1 minute cadence, right? Maybe that's something we want to work towards if it's something we really see as beneficial in the solar data. We could also think of stars that have really well characterized systems, for example, the HD 3651 planet proposed by the Brewer paper, and other things where the path might be dynamically cleared out or enough planets are found that we think we have a good understanding of the dominant planet signals. And even with the stellar surface, we saw that really interesting talk by Rachel Rotenbacher about how we are starting to use interferometry to image the surface of other stars that might give us the same information that we have for the sun. And we're benchmarking across instruments with a solar data set right now, but nothing is stopping us from doing a similar thing with other stars if we all decide to be friends, much as we have with the sun. And so this might be another thing we want to work towards as a group. And so really, the sun is a star, something I learned recently at the Sun is a Star workshop at the CCA. And there are many benefits for both sides of the coin. And so I put them in different colors, but I think there's many ways that we can bring these data sets closer together. And with that, I'll move on to the next section of this session, where Jen, yes, everyone's favorite face. Take it away, Jen. There'll be a timer up there.
Okay, you just made many of the points that I was going to make, so this is going to be short, which is wonderful. So in addition to looking at the sun and active stars, there's also a question of what can standard stars do for helping in these types of analyses. And so the solar RBs that Lily and many folks have talked about this week have highlighted the use of simultaneous observations and are a really promising way to distinguish between the changes in both our spectra and our activity indicators and the detectors that are due to the stars versus the instruments themselves. But it's maybe, we think there are challenges to relying on just the sun to do this work for us. Just a couple of examples. The reddest orders, especially for instruments that reach further into the red optical or near infrared, may not work as well because the sun is lacking in absorption lines there. So having a variety of stars and cooler stellar types might be helpful. And also, as I just mentioned, the sun is an extended source on the sky. It has differential extinction in a way that we don't see as much with other stars. It is having the solar feeds themselves, especially ones with domes on them, may introduce some level of additional systematics. And so there's a difference really in the solar data that comes into our instruments and the stellar data. And so it's important to have input from both of those directions. Now, simultaneous observations of standard stars from a variety of facilities, spectrographs, observatories are not going to happen by accident. That needs to be a concerted effort. And so we've started conversations about this in a standard stars working group that was just formed a month or so ago as part of the EPRV Research Coordination Network. I shouldn't oversell this. We have had exactly one meeting so far, much of which was trying to come up with an answer to what is a standard star. Because originally the way that phrase was used for many decades was stars that looked flat at the 1 to 2 meter per second level. And so you could use them to get a sense of how your instrument was performing, because our instruments were only reaching 1 or 2 meters per second. And so if the star looked flat, you called that good. Nowadays, with instruments that are reaching 30 to 50 centimeters per second, we don't think any star looks flat. But the idea behind this is still the same, right? The goal of a standard star is a way to calibrate the performance of your instrument on sky rather than in the lab via something like fiber tracking. So this is the whole optical system from, starlight coming down and hitting your primary all the way through to reduced radial velocities. And so because we don't expect the stars to be RV flat at a 50 or 30 centimeter per second level, we need a different selection criteria. And so some things that were discussed in this very first meeting of the Standard Stars Working Group was maybe making a grid of stars that span both spectral type and level of activity. Now that there is going to be an active stars or a stellar activity working group, maybe we hand off the active stars to you folks and keep just the quieter ones in the Standard Stars group. We'll have to think about that a little more. But I think this could be very nice, sibling efforts to figure out what we observe and how we observe it. And the basic idea we had for cadence was that we would want to monitor, whatever stars we come up with. The idea is, a handful, like 5 or 6 stars. Monitor them all at least once a month over a long-term, many years duration, so that we can look for things like signs of magnetic cycles stirring up in the stars, and then phase them in and out so that at any given time, at least one of the stars is getting as close to nightly observations as we can get between these facilities for an intensive month or 2 at a time. And so the idea that we've been thinking about going forward is writing kind of a community proposal. So everyone in the working group would contribute to a base proposal that can then be tweaked so that it is appropriate length and tone, et cetera, for different observatories. Folks would put it in through their institutional access, because it's a lot to ask the instrument teams to take time out of their own GTO programs to expand the standard star observing effort. So this is something that as a community we could help with and get our own time specifically for this science case. And then there's a big emphasis on making the data public on a very regular basis so that all of the working group members and also all of our broader exoplanet community members can study it, make use of it, do interesting investigations, and hopefully then report back to the working group on what they've learned along the way. Yeah, and then the other idea that was exciting was if we are observing the same stars with the same sets of instruments, to try and work towards doing cross reduction. So taking the raw data from one instrument, running it through the pipeline of the other instrument. And that would be another way to help distinguish what each pipeline is doing exceedingly well versus maybe a bit suboptimally, because at this point, all of our instrument pipelines are kind of bespoke creations, and it would be good to have an apples to apples comparison as much as we can with those. Okay, so yeah, I think that's the main highlights of this, and I will say thank you so much for your time.
All right, so yeah, I'm the last talk here, and Lily and Jen did some great job of highlighting a lot of the points I wanted to make. But maybe thinking about it from a slightly different angle of assessing our mitigation techniques. So this is a plot that we've seen a few times, or a version of this plot from Lily's paper. And really, we don't agree on what is stellar variability with our current mitigation techniques. And what we lack is a detailed understanding of when and why they disagree, or more to the point of this session, we lack these well understood, or a library of stellar data sets that we could use for assessing these techniques. Lily had a great slide that covered a lot of the points here, but how do we go from solar to stellar, and how can we match the ground truth, or how can we mimic the ground truth that we get from the sun in these stellar data sets? And another driving question is, in what ways can we extend what we've learned from solar data with interesting stellar data sets? And kind of the thought here is that with these deliberate studies of stellar variability, where we can choose individual targets that isolate individual sources of variability, either through target selection or through cadence, we can get these high fidelity stellar data sets. And so that's why this session here is sort of a push for stellar variability touchstones. We're sort of avoiding the word standards here, and you could maybe call these archetypes, whatever you want to call them. But these are observations of stars that are uniquely chosen to study single sources of variability. And just as a bit of a idea of what this might look like for some of the several different sources, targeting, say, young active stars, if you want to look at spots, or evolved stars if you want to study the effects of oscillations. And so it's these choices of target, along with how we observe them with cadence, that we can build up these types of data sets. And the reason we're here is because this is something that would take a community effort. We've seen in the solar data that our ability to trace some of these timescales is improved by collaborations between instruments, and in some cases, if the sources of variability that we want to study, it is largely going to be necessitated. For example, supergranulation. If you want to sample over many days, you're going to need longitudinal coverage, and that's something you can only get through multiple instruments. And then lastly, with these different instruments, we also are able to probe how stellar variability reacts in the, according to those specific instrument specifications, so wavelength range or resolution. And so that's something else that we're able to then probe on these with these data sets. And so Jen sort of was talking about the standard star working group and what's working there. So one possible framework here, this is a little bit more of a potential guideline maybe, where standard stars encompasses both these instrument calibrators, which were the sort of canonical standard stars, but also includes these variability touchstones, which can have some subsets depending on what type of variability you're interested in. But perhaps maybe we want to do something more in parallel, leave standard stars as kind of the instrument calibrators, and leave a variability to a separate group. So that's something that we're interested in sort of discussing here today, though I will say we are in this session specifically focused on studying stellar variability and getting deliberate stellar data sets on that side. So that's kind of the driving goals here for this session. At this point, we're going to transition to some group discussions. So radical idea here is we're going to be breaking the room up into groups. So be prepared to grab your computer or your things, and we will split up into groups. The people on Zoom, we will break you into breakout rooms, and we're going to be discussing a few questions. So each group, we would like if you could assign somebody to be a scribe or somebody to take notes, maybe multiple people to help out with that effort. And we also have chocolate here to help bribe people to volunteer for that. And we're going to go through a series of 4 questions. Each group will be discussing each question as we go through. And then at the end, there will be about 10 minutes with people within their groups to kind of discuss what they've talked about in each of the questions, and sort of prepare us a summary so that when we all come back as a big group, we can spend the final 20 minutes kind of talking about what everybody talked about in their groups. So without further ado, we're going to break up the room. So I think what we want, so there's not many people over here, maybe this whole side could be one group if that's okay. How many people are here in here? And then could we maybe start by splitting this section in the front and a back, and then the same over there, but there's not as many people in the front, so maybe some more people come to the front. So let's start breaking up, and yes, move please. Hello. Okay, so if anybody on Zoom, you should have received a notification to join a breakout room. Please do so. And we will be checking. I don't know who can hear me, but we will be sending the discussion questions via global Zoom breakout chats. So. Lily, can you send a global message? Tell people to volunteer to be a scribe. I guess we don't have chocolate for the remote participants, but they can write their names down and I'll owe them a chocolate someday. So the other thing for people here in the room, if you could also join the Slack channel, there is a link that has been posted to a document that has the place where everybody can take notes. And we will be numbering each group in the room, and you can find your group number on that document. So yes, group 1 up here in the front, group 2. Great. And if we could have volunteers for scribes, also that would be great. I've got chocolate. It's not Swiss chocolate. I think at one of the previous EPRVs, somebody had Swiss chocolate. Mine is just Dove chocolate, so I apologize. Okay, so it seems as though people are in groups. Hopefully you have assigned scribes or you all have that document open. We're going to go ahead and go to some of the questions now. But as you're discussing this first question, if you also need time to get people's names and fill those in, that would be helpful as well. So please go ahead and do that. But here's our first discussion question. So the question is, what do we want to make sure that stellar variability data sets capture? Oh, there's a thing on the screen. People can't see. I see. I don't see that, so I don't know how to change that, but people can, you can read. Yeah, this includes what types of variability and their relative priorities. It can include things about cadence or baseline of observations, anything from instrument specs to observations that support RVs like photometry, interferometry, and things like that. So go ahead and discuss. We will set a 10-minute timer. Thank you. What? I'm sorry, what? Yes, we will put the question in the Slack. Yes, the questions are also in the Google Doc.
You don't see it here.
No, I don't see it. But yeah, you have to like stop sharing and say no or something.
I saw your mouse. Can you like?
It's really hard to see.
I know. My mouse should be over there now. Can you see it? Okay. Okay. More to the left. I really can't see it at all. Okay. Oh, wait, I think I see it. Oh. Okay.
Enter your names there, and so the message about what you're discussing, we'll update those questions. The questions are also so you can start to discuss them. Oh, okay, yeah, okay, yeah. So it should be a template that you can okay, yes. All right. Yes, yes, entirely. Okay. All right, I'll leave you to it. The first question is about we want to make sure that stellar variability data set speaking to text variability gains the baseline respects for observations are I mean, are we trying to, I guess, what source of variability are of interest? So, we want to capture in terms of yes, yeah. Yeah, so I mean, it's sort of a right, yeah. So I guess yeah, this question is what do we want to celebrate? And yeah, that can mean a lot of different things. You can see Oh, yeah.
All right, looks like it's going really well by sleeping on the slides. We encourage you to finish up your thoughts on the first question and move on to the second question now. And so we'll switch the slide over, hopefully. Is it gonna work? To the second question, which focuses more on the sort of targets we should prioritize and why.
Hello, everyone. We are moving on to question 3. Feel free to wrap up your question 2 thoughts, but we will be moving on to question 3, which is what is our best approach to getting these data sets? This can include discussions about buy-in from the community, individual proposals versus, say, instrument teams, which kind of gets at public time versus GTO time. And then the question about is there a need to accommodate for these within standard STAR programs? But feel free to interpret this question as you wish and discuss.
All righty, ladies and gentlemen, we are now on to our fourth and final question for the session, which is, what have we missed? So we've given you some prompting questions to try and think of things, but if there's something that you think is relevant to this discussion that hasn't been covered yet, this is your chance to write that down and also maybe revisit something else that's been discussed. We're going to give you some minutes to do this, and then also some minutes to synthesize what you've been talking about over this session. Pick someone to represent your group for the report out, and we'll call you guys up, one person from each group, to present at 3:15. Yeah. Oh, and the person that gets to come up and do the report also gets chocolate.
Hello again. Just a reminder that we will all be coming back and doing our reports and summaries in like 3 minutes at 3:15. So wrap up and make sure everybody's prepared for that. All right, everybody. So let's wrap up here. Why am I hunched over so much? Okay, so if we could have each group's summarizers come towards the front. Please step forward. Thank you,
Right up.
Xavier. Oh, yes, you will be getting chocolate. I'm sorry, it's not Swiss chocolate, but.
It's subpar Dove chocolate, but it's still tasty. It's still chocolate.
But yeah, thanks. Let's group.
Haven't you have everything here? Oh, no, not really.
Oh, I have the, oh,
The
sorry.
Google Doc, you can access it on this
Hmm.
computer, or would be that's easier than having it.
Um,
Oh, no?
mm,
I know,
that's not a-
okay, no, sorry. It's fine.
Yeah, okay.
It's fine.
Yeah, that's not a, yeah. Okay, so what we're going to do is we're going to have each group, we're going to go through each question again and do a very quick summary of what each group said. So starting with question 1, Xavier, you're closest to me. So if you can begin with a summary from your group on question 1.
So what do we want to make? What do we want to make sure that stellar variability data set capture? So we discussed about like the type of like data and the type of stars we would like to observe. So there was some interesting discussion about spectropolarimetry. Okay, because of course, if you want to detect magnetic fields, getting the stock different profiles is the way to go. Then also there was some discussion that today, currently, we don't have at least spectropolarimeter don't have the same precision as what we can do with spectrograph that are not polarized. But perhaps the idea is that, okay, we can perhaps observe some stars with different instruments, some that are not with polarimeter, where we can really go down in precision there. And then perhaps also have some other observation, perhaps in the near infrared, of the spectral polarimetry. There is now some instrument like Spirou that can do that, and to really combine those two data set together. Okay. Oh. Okay, I didn't, okay, fine.
Okay, so quick rundown from group 1. We also want near infrared coverage. I might be biased on that. But we also decided that we wanted more simultaneous observations, maybe doing interferometry on certain targets, Doppler imaging. I think one of the key things that came up is looking for indicators other than calcium H and K and having data sets that can really do that in detail. That might need lots of data on a very small set of stars, but that could well be something we want to do with high resolution. But basically more data in various parameter spaces that people smarter than me should think about. There we go.
All right, so our group focused on 2 things, and I'll talk about one of them that we spent a lot of time discussing, which was the need for potentially data at higher spectral resolution. People were very interested in the talk Michael gave, showing how the information we can get quickly degrades as the resolution of the instruments degrades. And increasing that resolution might be something we need to do going forwards for these data sets, even though a lot of the current generation EPRV spectrographs don't quite have those capabilities.
So from group 4, we put a major emphasis on observing cadence, not only for resolving rotation periods, but also identifying and studying differential rotation. And then we also added in how new technologies can allow us to do this a bit more creatively, things like photometry with CubeSats to track individual stars over long baselines.
So one of the things we were talking about was that we should have a more photons and less time, essentially, because if you extend your observation too long, then you can smear out any variability signals that you might have. So if we do have the simultaneous photometric and spectroscopic observations, the spectroscopy might show an integrated time period over quite some time on the photometric side. So you don't know exactly what's driving your variability.
Thank you. All right, and to the online group, if you can hear us, do you want to go ahead and give a quick couple sentence summary of what you discussed under this question? I think Eric, you've been dubbed in.
Oh, okay.
Oh dear. So I mean, the obvious thing of lots of great data, we discussed a little bit varying across spectral types and the tough trade-off of we'd like to have multiple stars of a similar spectral type to understand differences on a small scale, but also the need obviously to go from F to G and K, and the difficult trade-off with the existing resources of not being able to get high cadence on all of those at once.
Wonderful, thank you. Okay, on to question 2. Now we're going to switch the order up. Eric, while we have you on live, do you want to go ahead with also summarizing what you did on question 2?
Well, again, there were kind of contradictions, things like stars you could observe all year round and stars you could observe from the north and the south. Stars that were RV quiet, stars that had some activity. We had things like photometric standards might be worth discussing whether they had additional value or not. A little just what can we do efficiently, and is there some way we can take advantage of existing stars from the programs they're already observing intensively, their high priority stars to reuse that, and could there be some nominal addition of resources to help fill out those lists so that there's higher overlap. And then I guess making sure we had very good representation around G stars so that we could compare the solar data to nighttime observations of other stars.
Okay, I'm going to now pass the mic on to group number 3, 4. There we go.
So we talked about the importance of like stars where we can take out some other things. So for example, focusing on stars where we have enough prior data to predict what part of the stellar cycle it's going to be in. Like if we know it's going to be a modern minimum star, for example, and how long. We also talked about targeting stars with TTV masses so we could cross-validate the RV masses that we're getting, especially for like young stars or stars with ultra short period planets. And then we also talked about like stars with oblique transiting planets. Yeah.
5. Yeah. I think our primary one was to prioritize targets that are being simultaneously observed with TESS or whatever space-based instruments are available. So that way you don't need an extra telescope just to do simultaneous observations. That was our big one.
So we had a long conversation about what spectral types, and we decided that big stars are irrelevant. So G, K, and M seemed to be where we thought was more important to focus on kind of these things, but particularly looking at different ages of stars, trying to get a better understanding of how the variability evolves with time. We also thought Barnard star is something we should still keep looking at repeatedly because we've got baseline data sets already, and maybe the instrument precision isn't there, but it will help get us a longer term understanding of what's maybe going on.
So our group focused on a few things. The first was, I think Eric mentioned this already, but observing stars that are equatorial and can be observed by all spectrographs, as well as polar stars that can be observed year round by telescopes in each hemisphere. And then we were interested in whether there could be some reason to try to observe stars where any planets we find could be, or any signals we find can be independently validated by other methods, because there's a lot of overfitting that you can do and find signals that aren't necessarily there with RVs. And if we can use other methods to observe this as well, that would be useful.
So yeah, so what I will not repeat also, I think equatorial stars is good because north and south, we can really have a coverage between all the different instruments. Tau Ceti is a good target, Barnard's is a good target, I think. We thought about Epsilon Eridani as well, because it's a star that is also that show more activity, but it's perhaps interesting for activity mitigation that way. And also, so we were thinking that, but we also, the thing raised, in a few years from now, there will be Plato. Okay, so we have to see perhaps if some stars could be in the Plato field where we could have continuous photometry for them, which would be a big help. And then also there is Cheops, there is the extension of the mission, and there is 1/3 of the telescope time that is for guest observer, basically. And through that, we would be able to get quite a lot of data for those stars. So, and also a final point, I saw some talks about SPOS, about NUID. basically a lot of stars are observed between, the same stars are observed between all these instruments. And those are also quiet stars. So we should talk all to each other, know which star we are looking at, just continuing, starting from those.
Cool. Okay. Right, on to question number 3. Let's start with Arvind.
Okay, so is this on? Yeah. So the main question for us was whether or not the right approach would be to have separate proposals through all the different tacks to get time through different instruments, or to try to find some way to get funding to buy in to all of them separately, so that we have guaranteed time, because there's always the risk when proposing through tacks that you don't get your time, or that your tack isn't, if you're banking on the fact that you're going to have time on every instrument, you have to have some way to prove that when applying for each individual instrument, and that doesn't necessarily always pan out. So we didn't agree on what the right approach was going to be. We didn't have a great answer for that, but we think those were the 2 approaches that would be possible, and we have to figure out which one will work.
Yep. I'll hand this over to Jonathan.
So I think we came to the same conclusion that basically someone in a coordinated way needs to buy telescope time, or there needs to be a funded call that's for an extended period of like 5 to 10 years to do this program, with all of the instrument teams getting enough telescope time to do it. So it's putting it on the individual teams and hoping it all pans out didn't seem to be a way to do it. And there needs to be a coordinated buy-in somewhere.
Great. Yep.
Came to a fairly similar conclusion, that we concluded that the EPRV community in general should act more like it was one giant consortium in prioritizing targets that are of interest to everybody, and it would be maximize our resources.
Yep. In Zoom land, Tom, do you want to give your group's answer for question 3?
Sure. Can you hear me?
Yep.
Okay, good. So like everybody else, we want more telescope time and spectrographs from money for that from NASA. We briefly wondered about whether it would be interesting to explore if there are useful criteria for optimally sharing or spreading cadence across instruments that can look at the same source, but our kind of gut feeling was that kind of political or practical considerations would probably already constrain that pretty fully without trying to work out some kind of formal decision theoretic best approach. One of the interesting ideas, so we echoed a lot of the ideas you heard already, but Mark Elowitz and Eric had an interesting back and forth about whether there could be a role for modest aperture telescopes, maybe even robotic telescopes. The issue is that they lack a spectrograph, but Eric kind of mused about whether we as a community could agree on some kind of standard architecture for a useful resolution spectrograph that could be produced in a multiple of a few and sent to some modest aperture telescopes at universities or someplace where they might be able to contribute to this in some way.
Wonderful, thank you. Xavier?
Yeah, so we had also a similar idea, but the thing that basically we discussed was that, okay, it's very expensive to build a spectrograph at the meter or sub-meter per second precision. And basically, if you go for a science case that is just to calibrate all the other instruments, it will be quite difficult to get, but okay. Now, one thing that I wanted to talk about was like how everything works a little bit in Europe, because everything is centralized through ESO. In fact, ESO has some open time for like things that are for the community. So there is 2 things. There is what they call calibration proposals, or there is public surveys. And in fact, those are time that you can request, and you can have for 4 years or for even up to 8 years. You can have really like a program that is for the community. The data becomes directly public. And this is the way we could go there. But those programs to be accepted, it should be really community driven. So all the communities should say that this is really the way where we should go. And I think what we're organizing here is is what we should do, and then go through ISO and say, okay, this is really what the EPRV community wants, and try to get sometime like that.
Yep, go ahead.
Yeah, so I'll be brief for the sake of coffee time, but I will say we also came to the same conclusions. There's a very strong consensus in our group that what we need is the data to be public quickly. It has to be high cadence and it has to be over long baselines, all of which are things that make it die in the TAC. So if we want this science to happen, this has to be at a higher level with some guaranteed funding and time.
Yep. Okay. Thank you very much, everyone.